Design afocal optical system. First, we need to talk about the terminology of afocal. What does it mean? A is a Greek prefix that usually when we put it before some kind of names, it changed the meaning to not having that element. For example, asymmetrical system means a system that is not symmetrical, or atypical is something that is not typical. And for afocal system means a system that doesn't have any focus or focal point. For example, in this optical model, we can see the beam is parallel, so it's not converging or diverging, so there is no optical focus before and even after the optical system, even if the beam can start from here. In both image and object plane, we don't have any focus point. So that's the reason that we call it afocal system, which means an optical system that doesn't have any focal point. Like here, if we focus on it, the beam comes from this side. It's a Cook triplet system, and we have a focal point here. But in afocal optical system, we don't have any converging or diverging point in none of the image or object space. So as I said, no net convergence. You can have convergence inside of your system between the lenses, between the objects and image plane. Not divergence, and the effective focal length is gonna be at infinity because you don't have any focus point in theory. So by a positive lens and negative lens, we can have a very simple, we call it Galilean telescope, we can have a very simple afocal system, but we need to put the lens 1 and lens 2 at a distance which is equal to f1 and f1 plus f2. If we do that, the magnification of this system, the magnification of this afocal system is equal to f2 over f1. And the total, we have an angular magnification. When you are talking about afocal optical system, everything is based on angular units. So in this case, one way to look at it is the angle of the beam for object at infinity over the angular divergence for the image, for the uh, image or object, or the height of the marginal ray heights at the object space over the height of the marginal ray heights at image space. That's another definition for magnification. So magnification is f1 over f2, distance is f1 plus f2. Now let's say when we have a optical system that we have some spec 3x Galilean monocular. Monocular is a it's like a binocular that you can see object at very far distance, but the main difference is that this is monocular. You only have one side optical system. You can put it into your pocket. It's very easy. Open it and take a look at the something at far distance. So let's say you want to design very simple Galilean monocular in Zemax. The input diameter of the beam is gonna be 50 millimeter. The length of the whole optical system roughly around 200 millimeter, which is about 20 centimeter, like this size. And the magnification is 3x. The lens thickness, because we're gonna build it based just by two lenses, the lens thickness is gonna be less than 30 millimeter or less than 3 centimeter, like this thickness. I mean, it can be, we can change it, but right now that's just the spec that we made for ourselves. Now let's jump into Zemax and take a look at this optical model in Zemax. So here in Zemax, let's start from scratch. Okay, new model. First things, as I said, we should take a look at aperture system explorer. So for aperture, we select entrance pupil diameter, And for aperture value, because the spec was 50 millimeter, I'm gonna put 50 uniform. I'm not gonna change anything. But one thing that we need to check is afocal image space, because here it's gonna change everything based on angular units. That's a very important thing that we need to check. So this item needs to be checked, and the field, we are not gonna change it. The wavelength is a default wavelength, 550 nanometer, which we're gonna optimize it for green light. Environment, we don't want to change anything. Polarization, so the rest is okay. Now let's look at our optical system. Let me put the cross section here. Okay, so we have object, the stop, and we have a stop and image. The definition of a stop is at the point that the maximum of your marginal ray height. So for that kind of optical system, because the rays are coming from infinity, the limiting factor in an optical system that limit the height of the marginal ray height is the input aperture of the first lens. So our objective lens, the mechanical things that is around it, or limit the size of the lens, any limitation, that's the stop of our system. So after stop, I'm gonna add a thickness, let's say 20 millimeter after stop. Doesn't matter that much, we can change it. So after my stop, I'm gonna add my first surface. So that's my first lens element. So here is my stop, this is my first surface. So for the comment, I'm gonna put E1, which is element 1, surface 1. And for the radius, I'm gonna leave it at infinity. The thickness, as I said, the thickness of the lens, we said less than 30 millimeter. Now I'm gonna put 20. And for material, let's select a regular material, NBK7 and BK7 available everywhere. So the rest, we are not gonna change it. That's my first surface. Now I'm gonna add my second surface of the first lens. So I'm gonna add another surface here, which I call it E1 as a comment. Surface 2, S2, again radius infinity. The thickness, so right now we are talking about the distance from a second surface of the first element to the first surface of the second element. So we said the length of the whole optical system is gonna be 200 millimeter. So I'm gonna put 200 millimeter here. I know you have 2 millimeter over there, 2 millimeter right there, but that's okay. So this is 200 millimeter. Now I'm gonna add another surface, insert surface after, which is E2, surface 1, element 2, surface 1. And for the thickness, as I said, let's put 20, the same as element 1. And for the material, let's select NBK7. So that's my second lens. First surface, let's add E2, S2, which is element 2, surface 2. And the thickness here is not that important because this is the afocal system. You can put your image anywhere. So, but I'm gonna just put, let's say 50, something that we can see. Okay, so that's my optical system. I have my object at infinity, stop, first optical element, the first optical element, and the second optical element, and the image. As you can see, everything is flat, the beam completely parallel. So in order to optimize this system, first we need to select our variables, what kind of parameters we want to change. So right now obvious things for me is the radius of curvature of these surfaces to make them like a real lens. So one option is to click on here and by mouse change it to variable. The other one is just click here, press V enter, V enter, V enter. So right now I changed all four surfaces as a variable surfaces for me. So right now I can change the Zemax can change the radius of curvature. But before that, before optimizing, we need to find the right operand for this kind of afocal system. You click on optimization wizard. So here we're gonna optimize it based on wavefront. The rest I'm not gonna change it. Click on OK. So those are the default optimization operand for this system. Before DMFS, I'm gonna add one operand. This operand is REAY, which is the real height of the beam. So I can click here. So that's the height of my beam at the image plane. So we can go to current operand, we can change it here. We can change those variables here, or we can change it directly here. Both of them are the same, but here it's easier because it's bigger and we can see it. So operand REAY, the color is different, the same. So I'm gonna put this operand for my image plane, which is right now my surface 6. So I'm gonna put it for surface 6, wave 1, and from HX, HY, PY, PX, PY. For PY, which is the height of the pupil, I'm gonna put 1 because it's in Y direction, and the weight I'm gonna put 1 for this operand, and the target we need to discuss it. As you know, the diameter based on our discussion and based on our spec is 50 millimeter. 50 millimeter is the total diameter, and the height of the top of the beam to the optical axis is half of this diameter, or the radius of the input, which is 25 millimeter. And now we want to have a 3x optical system. So it means that the height at the image plane should be 1/3 of the height of the beam at here. So 25 divided by 3 is 25 divided by 3 is 8.33. So I'm going to copy paste this number to my operand. The target which is the height of the beam at image plane is 8.3. I'm going to put a few 3 to make it more accurate. So right now I have my target, my optical system. Now we click on optimize. So as you can see in Zemax, when the merit function is high, it means that your system is far from the optimized one. So you're gonna start a few times. It goes quickly to a very small value. So right now it should be optimized. As you can see, this is my optical system. It's a 3x monocular system that the diameter here is 3 times bigger than the diameter here. And right now I can see I can change a lot of parameters and optimize it again. For example, the thickness I put for lens 1, I put the thickness 20. I can change it to 10. I can do the same. So but it's not gonna remain optimized. So I click on optimize. As you can see, the merit function goes high a few times. So right now optimized very well. The other things that I can change, for example, as I said, just select 200. I can change the length of the whole system. I can change it by, let's say, put 100. Now for sure it's not gonna be optimized because even by eye you can see it's diverging. So I'm gonna click on optimize again. The merit function goes really high. So yeah, right now the system is optimized. So let's put it back to 200 and optimize it again. Okay, now the rest of the system is gonna be the same. For analyzing, we can take a look at, for example, standard spot diagram. But here you can see everything is based on degrees. The spot radius diameter. Let me make it a little bigger so we can see it better. You know, all the legends and everything is based on degrees. We can take a look at our spot diagram. We can take a look at ray aberrations. Again, the scale is not like before. It's not on millimeter or any distance actually measurement units. It's based on angular measurement units. Right now it's 0.1 milliradians. So everything is changed to milliradians, but we can compare the system. Let me add the AV disk. Yeah, right now you can see I added my AV disk. Let's, for example, as a comparison, we can see um, this is a pretty good optical system, but I want to see, can I make it a little bit better? So let's change the thickness of the even I can put variables for one of them. Let's see what will happen. From 10, let's optimize it. So we can play and change all other parameters. Okay. Distance, we can make it pretty small, change the length. One thing that we can change is that, for example, we can make the first element biconvex, that two surfaces are in opposite direction. For example, this is surface 1. For the second surface, instead of V, I'm gonna use pickup, and from surface 2 with -1 scale factor. So right now I think it cannot optimize it again. Yeah, because in order to, I need to increase the rate of curvature that the focus passes that point. Let me put 200 for starting, even more than that, 300 for starting. And now let's see, can Zemax optimize it or not? Yeah, it optimized, because optimization is always looking around the solution that you provide. So right now it's a really good optical system because the spot diagram is smaller than the iris. So by changing those parameters and changing the height and everything, we can make our optical system, we can compare the optical systems together. Right now put 10 for each of them, and let's see the effect. Optimize it again, because our starting point is pretty good. Now let's look at the spot diagram. It's pretty good. Yeah. So yeah, we can change all other parameters, or the other way to look at this problem, we can find the lenses from, like, let's say Tor Labs or Edmond Optics, any kind of optical company. We can find the regular optics from there and set the thickness as a variable and find the best solution in Zemax. Thank you very much.